While most of us are used to having a desktop operating system that provides pretty good isolation between tasks, this cannot be taken for granted on a safety-critical embedded system and might not be enough. Let's consider a critical task in an embedded system. It needs to be able to use memory, CPU, a watchdog timer, hardware configuration data, the network, and other resources. It was almost certainly designed and validated assuming that all of these resources are available and are not being corrupted by external factors. Now introduce a non-critical task on the same hardware and ask what could go wrong. We need to assume that the non-critical task has a lower level of software quality because a less rigorous engineering process was used to create it according to the lower SIL assigned to it. That means that lower SIL task could have bugs that affect the operation of the critical task. The non-critical task could interfere with memory values. For example, it could accidentally modify variables being used by the critical task. If an interrupt service routine is designated at low SIL, it could overflow the critical task stack if it is activated while the critical task is running. And a non-critical task could have a memory leak, exhausting heap memory so that when the critical task needs some memory, it suffers a runtime error due to heap exhaustion. Non-critical tasks can also interfere with CPU use. The non-critical task could, for example, run at a high priority and starve critical tasks so that they never get a chance to execute. It could also disable interrupts, delaying critical task interrupt service routines, or even the operating system's ability to switch tasks, thereby causing critical tasks to miss their deadline. A non-critical task could compromise the watchdog timer by, for example, kicking it in a tight loop even though the critical tasks are all dead, or even disabling the watchdog entirely so that the system will never reset even if everything dies. A non-critical task can corrupt system operation by, for example, changing the direction of a digital output pin used for critical operations to instead be a digital input pin. Finally, a non-critical task could send bogus network messages that spoof the values of critical messages simply by accident, causing the system to be unsafe. Of course, not all systems are exposed to all these problems, but the point is that these problems can occur, especially with low-end CPUs used in cost-sensitive products. To be safe, you need to be sure these problems cannot happen with your system.